this video is on queuing theory. And first of all, before we look at an actual example of the queuing theory, I want to quickly run through some terminologies that are used in the queuing theory because they are very key even as you attempt particular questions. So to get underway, I'll start with one of these common symbols that they call lambda. Lambda simply means the arrival time. That's what lambda means. Then there's that symbol that looks like, should I say letter U, but it's called as mu. This one is the service rate. Just take note of these terminologies. They are very key as you even attempt questions because they usually base their questions on such wordings. Okay, the service rate. There is what they would call the inter-service time. The amount of time it takes to service one person. This one is determined by this formula, 1 over u. So since we already explained u, you now know what you substitute there. 1 over u simply means the inter-service time, the time it takes to service one person. That's what this one means. Then there's another one, another symbol you should be familiar with, is what they call the traffic intensity. The traffic intensity is denoted by what they would call rho, which is just simply equal to lambda over u. Okay, that's the traffic intensity. So if you are maybe being asked what's the probability that there will be maybe 4 people at this particular time, we would use this approach, this formula, to determine that particular probability we're being asked for. So you just have to like substitute, lambda, you now know mu, you now know from this previous explanation in the earlier part of the video. When you're asked for what's the probability, okay, you find some people there. That's basically what this one denotes. Or the other way they would use is traffic intensity. Then there's now another one I want to quickly write just after this. There's what they call idle time, the chance that the till will not have any people. So idle time is actually just equal to 1 minus lambda over mu. The chance that there will be no people on the till, that's idle time. So take note of these things because you might just be asked what's the probability that there will be no people on the till. So usually the approach we would take in such a scenario, when you're asked to now calculate the probability of no people maybe on a queue or particular maybe scenario, you would have to write this formula for probability. So when they ask you maybe what's the probability that okay you have at least 3 people, what does that simply mean? Just that statement, at least 3 people, meaning 3 or more. You can have 3, 4, 5 and so on. So usually when you begin with like at least this, or what's the probability that you have a maximum of 5 people arriving at your counter? That's going to be like from 0 to 1 to 2. Okay, so okay, this says 0, 1 and 2 and 3, 4 until 5. That's the number, a maximum of 5 people. So when you've got that, they would call this the probability of having n number of customers that you don't really know because they've just told you maybe at least or a maximum of this, so you can have a number of people. So usually the formula that denotes that is rho. If you rewind the video, you'll see what this means. Rho raised to the power n multiplied by 1 minus lambda over mu. So this is the one formula we use when you've been told, okay, what's the probability that at least this number of people should be there, or not more than 5 people should come. So you have, okay, 0, 1, 2, 3, 4, 5. Then you start computing the n. You'll be just substituting, since you've got like a list of numbers, for example here, right? On the n, that's what you'll be putting there. Okay, what if it's 3 people? You find the probability. Okay, what if it's 4 people? You substitute what there's a comma n there, the power n, and so on, until you come and sum up all their probabilities. That's what happens there. There's what they call the average number of people that are in a system. Average number of people in a system. So average number of, should I just say, people in a system. This one, the formula we use for average number of people that are in a system, we say lambda over mu minus lambda. So at this point now, you know all these symbols are now just substituting. Basically, that's what's happening at this point. But what happens is that you need to know the keywords. When they ask you average number of people in a system, that is just lambda over mu minus lambda. We said lambda is the arrival time, mu is the service rate. So you look out for such terminologies before you substitute in such a formula. Then they might ask you average time of people in the system. That could be another way they would phrase it. Average time, this time around time. The average time of people, or the time that people are spending in a system. So this one, when you're asked the formula that we just use in such a scenario, people in a system. Okay, so this one, we have a very, very similar formula to the one we recently drew. It's lambda over mu, open brackets, again mu, minus lambda. That's just like that when you're asked for average time of people in a system. Okay, now they might ask you something else, like average waiting time of a particular customer. You've heard how they phrase a particular, like one person, average waiting time of a particular customer. There's also a formula for that. Average waiting time of a particular, I'll just start from the P there, of a particular customer. Okay, so a particular customer, their waiting time, this one, it should be 1 over mu minus lambda. That should be the average waiting time of a person in the queue. Okay, how about the queue length? It's another way they would ask you, what is the length of the queue? Or should I say the number of people that are just in the queue and not yet being serviced? That's another way they would ask. So the length of the queue, or the average number of people that are waiting to be serviced. So this one, average number of people, average let's say average length. Let me just write that word. Okay, length, or should I say people waiting in queue. They didn't specify in the queue, meaning they haven't yet been serviced, they're just waiting in that queue. So you want to also determine the average length, or the the waiting, that queue. So we'll just say, okay, L, we'll just put L, okay, denoting, I'm sure, length there, is equal to lambda squared, lambda, the same lambda, you know, just square it now, over what? Mu, open brackets, mu minus lambda. That's the formula for average length of the people that are in that particular queue. They are waiting to be serviced. So take note of these terms, because when we look at a question now, we'll just be applying everything I've just talked about right now. So let's now look at an actual question. Look at this question. A repair shop attended by a mechanic has an average of 4 customers per hour who bring small appliances for repair. The mechanic inspects them for defects and quite often fix them right away or otherwise render diagnosis. This takes him 6 minutes on the average. Okay, then they told us that arrivals are the poison and service time has the exponential distribution.
You are required to find the proportion of time during which the shop is empty. So we want to find the proportion of time when the shop is empty. It's as good as asking for the probability that the counter will remain idle. So that formula we use is supposed to be 1 minus lambda over mu. So I'll come and write it very soon. What is lambda? Lambda, we said it's the arrival rate. You should still recall from the intro of our video. So the arrival rate, how do we know it from this data? They are saying that on average, there are 4 customers per hour who bring their small appliances. So that same word bringing is like people are arriving to bring stuff. So that is the arrival rate, the 4. So we know lambda. How about mu? Mu is the service rate. Mu stands for the service rate. So it takes average about 6 minutes, to service this diagnosis and giving a diagnosis and whatnot. So that is the service rate. So the only difference is that since they were viewing the arrival rate per hour, let us also equally change our service rate to also in terms of hours. So it's like when we're solving this, it's much, should I say, they're in line. They're all having the same details. So part A, we solve for how to calculate that the shop, it will be empty. Okay, so just before we substitute now on mu, we want to know mu, because on the lambda we know that it's going to be 4 people, should I say, per hour arriving to bring their items. So mu is just the service rate. So again, as the 6 minutes that he spends. So realistically thinking about that, that is actually the time he's spending to talk to 1 customer. So if you remember in the earlier part of this video, I specified that, okay, there is a formula for inter-service time, which just stands for the time that this person is taking to service 1 particular customer. The inter-service time is equal to 1 over mu. So the only way we would get mu accurately is first of all substituting, using this formula to help us get mu, because what is given in the question is the time he is just spending to talk to 1 particular customer. So 6 minutes is not yet in hours. To convert this, we divide by 60. What does it give us? 0.1. That's the one we come and substitute here, because as we said, this formula just stands for 1 over mu stands for the time that is done, or 1 over u or mu is equal to the time that someone is spending to service 1 customer. So just, you cross multiply, you should end with 1 over 0.1. This is what you should end with. If you divide that further, it's 10. So meaning this will be now your mu. So now will be equal to your mu, because we said the 6 minutes you're seeing in the question is the time that they spend on servicing 1 person. In queuing, there's a formula to calculate the time that is being spent on servicing 1 particular person, which is 1 over mu, and mu is a key component in the formula you're seeing above. After you get your mu, just erase what I've just written below. You just substitute, okay, now mu has been calculated to be 10. So we just say, okay, 1 minus 4 over 10, because we're now trying to calculate the proportion that the shop will remain empty. It's like it's as good as finding the probability that there will be no one or it will be idle. So it's like 1, this is divided by that is 0.4, right? So you should get 0.6 as your answer, that the shop will remain empty. This is the answer here. Part B. Part B said, I'll just try to recall it right now. Part B said the probability that at least one person enters the shop. The probability that at least one person enters the shop. What formula do we use for that? Well, when calculating probabilities that, okay, at least a certain number of customers are entering, I said something like this, I think in our intro, that you say, okay, rho, we said what rho meant. Rho is just lambda over mu. That's what rho meant. You recall, again, you wind in our video, multiplied by 1 minus lambda over mu. This is the formula we use when calculating probability that, okay, a certain number of people, like if you're told maybe 3, 4, 5, like the probability that, okay, at least between 3 and 5 people will come. So you get for 3, 4, and 5, then you sum up their probabilities. Now here they're telling us at least one person. At least one person. What does that mean? Just that statement, at least. Meaning one itself and what? Anything more than 1, 2, 3, and so on. They haven't even given us a limit. That's the downfall of this question. They haven't given us a limit. So what do you do? In probability, how it is that if you have not been given a limit of something, right, the only way you would get an accurate probability value is that, okay, get the probability of the numbers that are less than 1. That's usually the trick. You get the probability of the numbers that are less than 1. When you subtract from 1, it will give you the answer of this one, which is greater than 1. That's the probability. That's the theory we use. So, for example, if they told you, what's the probability that at least 3 people will enter the shop, meaning 3, of course, going on until maybe infinity. So the only way you'd get an accurate answer, because this other one has no ending, get the probability of everything that is less than 3. Maybe 1, okay, not 3 itself, maybe 1, just 1 and 2. 1 and 2, you get their probabilities, then you go and say 1 minus that, because all probabilities add up to 1. That's the theory which works here. The probability of the event being questioned and the probability of the event that it will not occur, it should always add up to 1. So in this case, the event we want is the numbers that are at least 1 and going further, and then the event that we do not want is less than 1 if you've picked this. So basically, let's look at less than 1, which will help us get the answer for at least 1, which is the other side, 1 and greater. So which is very simple, because if you look at any numbers that are below 1, it's just 0. Meaning we already just been calculated it previously, because the probability of 0 people, you will just say on your row power 0, meaning the answer is what? The answer is 1, right? Go to this part in the brackets. Anything in the power 0 is 1. Got this stuff in the brackets. It's 1 minus lambda over mu. If you remember this expression, was just from solving an equation about that on idle time. So it's like 1 multiplied by, the answer we found was 0.6. Yeah, which is just 0.6. So we already know that, okay, then the probability is, okay, less than 1 is 0.6. What about those that will be at least 1 and greater? It's just going to be like, okay, probability, we're just going to do this. It's just going to be 1 minus that probability that, okay, those numbers that are less than 1, which gives us 0.4. It's just as simple as that. We just try to reason on that using the probability theory that, okay, the required event plus the unrequired event, they all add up to what? To 1. Probabilities always add up to 1. Okay, so that's the answer for B, just like that. Let's check C. C says the average number of customers in the system. There's a formula for this one as well. But D says the average time including service spent by a customer. So I want to find the average number of customers in the system. Number of customers in the system. So let's go to the next page again. Then I show you the formula for that. The average time the average number of people in the system. This is the formula. In the system is the keyword. This is the formula we use. Then you just substitute. Lambda is 4. Mu, we've just found it's 10. 10 minus 4 is of course the 6. So if you divide that, what would be your answer? 4 divided by 6 should give you, it's recurring, 0.66 and the like. I'll just shorten it to 67. So even though your answer comes out as a decimal, we just record. I know you might not really see this as realistic, 0.67 people. Yeah, but we just record according to queuing theory. Even decimals count. Let's go to part. This was for part C, by the way. We have solved part C. So now part D said the average time spent by the people in the system. So the formulas are not even very different. When you talk about time, we just add the mu here. If you've noticed this side on the left, I've just added the mu to the equation. And then you just go back and solve. This is for time. By the way, we're solving part D now. We said for time. So we said lambda is 4. Mu is 10. Open brackets, 10 minus 4. This gives us, of course, that would be 6 in the brackets. 6 times 10 is 60. If you divide that, what does it give you? The 4 over 60. 0.067. It's recurring, just end there. And basically that's how you handle these questions in should I say queuing theory. They're just straightforward. What matters is know your formulas well, and you can easily substitute in any given scenario. Yeah, so kindly go through from the start of this video and get to analyze all those key terms. And that was the video on queuing.